So thanks for Dimitri for the kind of introduction. And as you see, exactly the simple and explicit, so you know what I'll be talking about. And I'm afraid I want to welcome you, but also to congratulate you. I'm sure some of you in the back of the mind came here fearing to cope with this kind of seminars, with this kind of slides, one after the next, and thinking, oh, I'm sure it's beautiful, but the beauty of it eludes me totally. And I'm sorry, really, to disappoint you, but it's not what you'll be getting. In fact, you know what Dimitri mentioned? He said two things. He said theory, and he said basics. So we'll be back to basics. So what we'll try to do is much more simple and close to the ground. Essentially, what I try to do is to help you follow more or less on not really hand-waving basis, but a simple, you'll see every equation, but just a couple. The strict minimum, but what's useful for you to follow and answer a few questions. For instance, we've heard in the previous introductory words that you'll be doing measurements. You came with your sample, most of you, in the appendix tube at the right temperature, and you will be putting it into a SAXS measuring cell. Then someone will open program, of course, nobody's doing anything with beamlines nowadays. Will open the shutter, meaning that the X-ray beam will just shine onto your sample and something will happen. So we'll try to say a couple of things about what happens in the interaction between your X-ray beam and the sample. And there is a detector at the end to recall the so-called scatter intensity. And we'll try to also understand why you're not going to get this kind of result, a series of sharp diffraction rates. You're not going to get either this kind of probably more familiar protein diffraction crystals, the 2D array of sharp, more or less sharp diffraction spots, but something which at the end of the data elaboration will look like this. It will sum up into a so-called SAXS pattern, continuous one-dimensional data set. And why is it so? And then in the next stage, we will try and see how from this SAXS pattern you can derive structural parameters such as molecular mass or GD max V. This is possible using some laws, physical laws, which have been established by scientists, the first of whom you heard the name already from Dimitri, André Guinier, but there are many others. And you will hear about those laws on the physical basis, and also always forget that physical laws are always associated with assumptions. You assume you're in this and that case, your sample at this and that cocktail, and given this and that cocktail, then you can derive this and that parameter value. So, and I will insist on this. Basically, I'm the not really bad guy, but the boring guy. I will keep on telling you, mind this, you should always check this, you should do that, and so on. While all the others in the next days will just show a wonderful display of wonderful programs allowing you to derive ab initio shape, do hybrid modeling, and learn a lot of things which, with luck, can even be relevant to the biology and molecular function of your molecule of interest. So what I'm doing here is just to prepare the ground for you to take full benefit. And the general outline of my talk is very simple. It's three-tiered. The first tier is just a reminder of elementary tools and notions. So we'll see X-ray scattering by an electron at the origin, simplest case possible, X-ray scattering by assemblies of electrons, and then I'll tell a couple of words on the Fourier transform and on the convolution product. The things you've already seen during your training, but you probably don't use them every day, so you've forgotten about it. So what I'm going to do is a refresher course, basically. The second part will be more focused about what we'll be actually doing, that is studying SAXS by particles in solution. And here we meet the notion of contrast, the notion of spherical averaging, monodispersity, and ideality of solution. And finally, in the third part, we will get into the details of data analysis and how you can derive this and that parameter, this and that property of your molecule by studying your scattering pattern. So let's get started with those elementary tools and notions. And really, the first slide, we need a starting point. So we'll start with the simplest possible case in dealing with scattering of X-rays. It's the case of elastic scattering by a single electron. Elastic means that the interaction occurs without exchange of energy, so that the scattered photon has the same energy or wavelength than the incident photon. There is no difference between both. It's just the direction of propagation which changes. And this is the intensity elastically scattered by an electron placed at the origin is given by the Thomson formula below. And as you can see from the dates of J.J. Thomson, it's not the last Nobel Prize. It's just the one before. So the intensity is given here. I of 2 theta equals r0 squared 1 plus cosine squared 2 theta over 2 1 over r squared is 0. So it's fine, but what are all those parameters? 2 theta is the scattering angle. And as you see on the diagram on top, not theta, 2 theta is the scattering angle. So just to note, in the case of small angles, then cosine 2 theta, as you know, will be close to 1. So that the ratio 1 plus cosine squared 2 theta over 2 will be close to 1 as well. Just trivial, but just to help you, not let you doing the whole job. I0 is the intensity of the incident beam expressed in terms of energy per unit area per second. And finally, R0, the first term, is equal to E squared over MC squared. And you have its numerical value, and that's the so-called classical radius of the electron. E is the charge of the electron. M, the mass of the electron. C, the velocity of light. And here already you understand a couple of things. First, you understand why for X-rays are scattered by electrons and not by nuclei, which are the content of matter, or atomic matter. Because a neutron has no charge, so it won't scatter X-rays, and protons have a mass which is typically of the order of 2,000 times that of the electron. So clearly, the scattering by protons will be negligible. So all what matters for X-ray scattering are electrons, and that's why from now on we will be only speaking about electrons. And this will be a major difference with a subsequent talk by Psi. We'll be presenting neutron scattering, and neutrons are scattered by nuclei. And you'll see in a second, so another related major difference. So I introduced 2 elementary notions: the differential scattering cross-section, d sigma over d omega, which is essentially this product. At small angle, it's close to r0 squared. And what's called the scattering length of the electron B, which is B squared is d sigma over d omega, so at small angle, it's close to r0. Immediately afterwards, I will introduce the notion of scattering factor. And the scattering factor, f of an object, is defined as the ratio of the intensity of the amplitude scattered by an object and that of one electron under identical conditions. So that, by definition, the scattering factor of a single electron is 1, since it's a ratio of 1 electron over itself. And the advantage is here we will simplify your expressions, because we eliminate d sigma over d omega from all expressions. So we simplify things. Now, you will ask me, and rightly so, why do I bother wasting 1 minute, precious minute, to introduce d sigma over d omega? Just with the next slide, I will eliminate it. again, is just in relationship with the next door quasi, because between when we study neutron scattering, neutrons scattered by nuclei, from one atom to the next, the scattering length and differential cross-section for neutrons vary widely, which is a factor of complexity, but also a very interesting property of neutrons, as you will see in the next talk. But I wanted to show you that from the beginning, the formalism is the same, and it's the same physics, with, of course, some clear differences in the particles that are actually scattering. Now, let's go to the second simplest case, scattering by an electron at a random position, generic position R in space, with O the origin. What are the consequences of moving the electron from O to M? Vector defined by the vector R in red. If you look at the path difference between the two rays going through the origin and through M, you see it's very, very elementary. It's the difference R scalar U1 minus R scalar U0, where U are unit vectors defining the incident and scattered X-rays. So it's R scalar U1 minus U0, and this corresponds to a phase difference phi equal 2 pi R scalar U1 minus U0 over lambda for X-rays of wavelength lambda. Good, very simple. Now, we will look at it. It looks different, it's exactly the same thing. But here, what we'll do is, again, to simplify expressions. We'll be using, instead of unit vectors, we're using the so-called wave vectors K or Q, depending on authors, where that have moduli K0 equals K1 equals 2 pi over lambda. Then the K1 minus K0 difference is denoted Q, the red vector. And the modulus of this red vector Q is equal to 4 pi sine theta over lambda. You'll have 30 seconds playing with this and you see it's evident. It's just elementary trigonometry. So Q, the so-called momentum transfer. So that finally, the consequence of moving the electron to a generic point at position R is to introduce a phase difference phi equals Q scalar R. So you see that this expression now is much simpler than that we had before. Sorry. Some authors prefer to use a scattering vector S. The moduli is S equal to sine theta over lambda. So the phase difference here is phi equal to 2 pi R scalar S instead of Q R or RQ. Never mind. So the 2 pi is explicit here. It's just a matter of choice, of convention, it's no problem. Just a word of caution, because some authors prefer to use S to designate Q, which is, to my mind, pointless source of confusion for readers of authors. But since this group is that of Patrice Vachette and others, they have two main, say, qualities between inverted commas, namely properties. First, they are hosts, so we have to be kind and cordial to them. And second, they represent a noticeable fraction of production, both in terms of tools, methods, and results. So we can't ignore them. So the bottom line message that you should take home and never forget about it is to, each time you read a small scattering paper, the first thing to do is just to check what is the convention used by the authors. And don't just rely on S equal to sine theta or Q is 4 pi sine theta. Okay, now we'll get into some more complex things. Not one, but several assemblies, some more impressive, assemblies of electrons. And here, one has to distinguish very carefully two very different cases. The first case is the case where the distance delta between scatters is fixed. That is, for instance, atoms within a molecule. In this case, since the distance is constant, there is a constant, well-defined phase difference between the two scattered rays. They would interfere. It's a case of coherent scattering, and one will add up amplitude. So f of q scattered by the assembly of electrons is, or of atoms, is sigma of fi exponential I or I q. We're summing up all scattered scattering amplitudes, where I the position of atom I with f its scattering factor. We can also describe the object, the assembly, by a continuous electron density rho of r. And then we have an integral expression, f of q equals sum of rho of r exponential r q dvr. But of course, we never measure experimentally the scattering amplitude, we measure the intensity, which is, as you know, the product of the scattering amplitude by its complex conjugate, f star of q. The second different case is that when delta is not fixed. For instance, two atoms in two distant molecules in solution. Then there clearly is not a constant distance because they are moving in solution between the two atoms. And it's a case of incoherent scattering, and then one will add up intensities. So I hope this is very simple, but I hope it's clear, because we'll work using both cases constantly, first in the rest of my talk, and then subsequently more or less explicitly in all what comes later. So some of you who have some mathematical culture, elementary, very basic, I told you it's so actually basic, have recognized this expression as being the Fourier transform of the electron density rho of r describing the scattering object. So the scattering event can be associated with a transform. You start from the electron density that describes your object, and you end up with the scattering amplitude, the Fourier transform, through a Fourier transform. Good. So basically what I've done is to give it a name, but it's useful because 100 people have worked about the properties of Fourier transforms, so we know what we're doing. It's not something totally wild we have to model. It's very well known ground. Now, there are two properties I want to introduce of the Fourier transform. The first one, that is linearity. The Fourier transform is a linear transform, which means the Fourier transform of a linear combination of two functions, ρ1 and ρ2, is the same linear combination of their respective Fourier transforms. Again, elementary. Sorry. What have we done? Oh, hello. Good. Yes. And the second one is the value at the origin of a Fourier transform, f of 0, so q equals 0. Then the integral is equal to rho of r dvr. It simplifies down to this because the exponential term, whatever r, is equal to 1, since q equals 0. And this is interesting. The electron density associated with the particle integrated over the volume gives you the number of electrons of the particle. And experimentally, you never measure F0, you measure the intensity. So the intensity at the origin scattered by your particle is the square of the number of electrons. It's simple, trivial, but it's important, and we'll come back to it later. So now we'll introduce something you might be less familiar with, the so-called convolution product. So a convolution is an integral that expresses the amount of overlap of a function b as it is shifted over another function a. The mathematical description is written here. You denote the convolution product by a star. So a of r star b of r is sum over vu of a of u. The u is the integration variable. B of r minus u, so we invert the function b, it's not B of U minus R, B of R minus U dVU. And I'm sure to most of you it tells you nothing. You look at this and you say, yes, big deal. So we'll first look at a very simple case, the simplest possible, I think, or close to. A case of two step functions, two rectangular functions. One A of R, the brown one, which is constant from minus RA to plus RA, and B with corresponding RB, it's a bit narrower in this case, and the top value is 1, the constant value. And we will show that the convolution product is the red profile you see with this trapezoidal shape. Okay, so it will help you. And we'll see it very concretely. So this is a one-dimensional case to make things very simple. So the only snag with this a simple case, so I will correct for it in the next slide, is that we first invert B, and you can't see it because B is symmetrical. I'll tell you later why it's symmetrical. So we take B of R minus U in green, and you see at large negative values, you can integrate over U. There is not a single value of U where the product B of R minus U and A of U is non-zero. Either B is non-zero but A is 0, or the opposite. So convolution product, even after integration from minus to plus infinity, is 0. Up to minus RA plus RB. Then we see that there starts to be an overlap. And you see that it will start to give you this, the sign overlap in volumes here, and it will increase linearly for obvious reasons, since it's just moving linearly with the value R, and up to minus RA minus RB, at which point we have full overlap. And since B is 1, then the value of convolution product will be that of A. And it will remain constant because it's full overlap till, for symmetry reasons, RA minus RB, at which point it will start decreasing linearly to RA plus RB, and then it's identically linear. So this was simple, and I guess you start now getting a feeling. I don't ask you to calculate complex multi-dimensional convolution products, but just to get a feeling about it. And now, thanks to a colleague in front of mine, Philippe Dumas, who worked at Strasbourg, and during the French Biophysical Society, they gave us a talk dedicated to the memory of Joseph Fourier, the Fourier transform, because Fourier has been born in 1768, so 250 years ago. And within this talk, he introduced the convolution product. And he's done the thing thoroughly, so it's not my work. He did the whole calculation and produced a nice figure. And here you see a general case, no symmetry, nothing. F denoted the F and G and J, X instead of R, I mean, just notation. And you see the first one, F in blue or violet, as a negative trough, and then go through 0, and then a maximum positive peak, and then returns to 0. While J of X in purple is what one could call an asymmetric, not really Gaussian, but bell-shaped curve, okay, with finite bases, 0 and 0. And then we will start to do the convolution product. So the first thing we do, as we mentioned, is get the symmetry G of minus X in purple. And now you will see the whole calculation, not this, but the next slide is done. You will see on 3 figures on the same slide, and they will be moving, some animation. So that's why I presented beforehand, not to play 10 times. So on top, you'll have J of minus X moving, sliding over F, which is fixed. And in bottom left, you will see for each position the product J of U minus X and F of X. And in the final one, you'll see, corresponding to each position, the integral over this product, giving the value of the convolution product. Okay? 3 figures, it's all moving, you concentrate, and you look at it. So, G is sliding, here is nothing, and here you can start detecting the convolution product, and here, the product of the two, and the convolution product. And it's a lot of work to do that. Well, not a lot of work, I'm happy he did it. So he gave it to me, and I'm happy to show it to you. And what you can see here, if you compare A and H, you see that the convolution of A and B has essentially smoothed out the features of F. Sorry, F and not B. The blue curve turns to the dark one. There is the same, qualitatively, the same curve, but simply the negative and positive peaks are broadened and smoothed. Okay, and that was the same thing with the 2 rectangular profiles, which ended up in a trapezoidal profile. So we're smoothing out things. Good. There's one property which is very interesting. The Fourier transform of a convolution product is equal to the direct product of the two respective Fourier transforms of A and B. And reciprocally, the Fourier transform of the direct product of A and B is the convolution product of their two respective Fourier transforms. And this is very useful, and you see a direct application of it in 10 minutes or so. Now, we'll look at a specific case of convolution product called the autocorrelation function, well, meaning of a function rho of R. So it's denoted gamma of R, and it is the product, the convolution product, sorry, of rho of R and rho of minus R. And it's written, it is again an integral of rho of R plus U, rho of U dvu. So that's fine. You derive this from the previous one just by changing the variable. It's trivial. But then let's focus on the specific case where rho of R is constant, a uniform density particle. Rho of R equals rho whatever R. So here you can derive rho, you can extract factor out rho square from the integral. And you understand exactly the integral of dvu, what it is. It is the overlap value, the volume common to a particle, which we're studying, and its ghost in sign shifted by a vector r. And you see in green, with transparency, you see this common volume, the overlap volume between the two particle and its ghost. And we see that, so gamma of R is rho square, the overlap of R, and for 0, we have full overlap, so gamma of 0 is rho square V. Of course, again, in the case of a uniform density particle. So where basically the integral turns into a geometrical integral. Now, we can also consider, associated with the autocorrelation function, the spherical average of this function. As written here, gamma of R, where R is a scalar, it's the modulus of the distance between 2 points, the modulus of the vector, and we average, we're putting together, averaging all gamma of R's, all values of the autocorrelation function with the same moduli, whatever the direction. Then we can define a so-called normalized case version of gamma of R, which is gamma of R divided by gamma of 0. We denote gamma 0 of R, it's not very original, and it's called the characteristic function associated with the particle, because you are always talking about one given particle, and here uniform density. Gamma 0 of R is the probability of finding a point within the particle at a distance r. We're only talking of distance now, spherical averaging, moduli of distance, from a given point. And indeed, by definition, gamma 0 of 0 is 1, and it befits it's in agreement with the probability notion, because you're sure to find a point at the distance 0 from this point, it's the point itself. So no big deal. And the profile will depend, of course, on the specific shape of the object, but whatever the size, whatever the shape of the object, one thing is common to all particles and all characteristic functions: they will admit an upper bound, because whatever the particle, you can define the maximum distance. There are 2 points, or several couple of them, never mind, the sphere, for instance, where the distance is maximal. We call it Dmax, again, it's transparent, and beyond this, by definition, there is the probability is 0. There is no pair of points, since Dmax is the maximum. Okay? So it seems trivial, but you see later on that it's really very important. And I will conclude with the last notion or function I will introduce related to the previous one, and we'll see how it is related. The so-called pair distance distribution function, P of R, which is the distribution of distances between all pairs of points within the particle, weighted by their respective electron densities. So you have a particle, you have 2 elementary scattering volumes, I and j, measure the distance, R, and you will add rho I, rho j, the product of their electron densities, as a weight in the bin for histogramming, which corresponds to R. Now, of course, in the case of uniform density, then it's rho square, and you can factor it out, and then it's just a scaling factor, basically. Now, we've seen what gamma 0 of R is, the probability of finding within the particle upon j a distance R from a given point I. But now, we are interested in the distribution of distances, or the number of distances. So the number of elementary volumes I is proportional to the volume of the particle. The number of elementary volume j at a distance R from I is proportional to R squared. The area of the sphere centered into I of radius R, so that the number of pairs ij separated by the distance R is proportional to R squared V gamma 0 of R. So finally we see the relationship between P of R and gamma of R. P of R equals rho squared, the electron densities, gamma 0 of R, V R squared, and this is essentially gamma of R, so that P of R is equal to R squared times the spherical average of the autocorrelation function. And you'll see why we are always doing spherical averaging in a minute, because it's what is important for what, relevant for what we're doing. So much for this introduction to elementary motion. Now we'll focus on the case of particles in solution. So we've seen that the particle is described by the associated electron density distribution rho P of R. And you see here the typical diagram symmetric representation of a typical protein with its electron density average 0.43 electron per cubic atom or so, and small fluctuations around. But this is macro, okay, just the absolute number of density, electron density distribution. But we are not in macro. We are doing our experiments in solution. Solution is a surrounding solvent, which is essentially water plus a bit of varied molecules for buffering and stabilizing defining the ionic strength. So that essentially we have water around with its electron density 0.335 or so, and we see that now what will matter for X-ray scattering is the contrast of electron density between the particle and the solvent, delta of R. Okay? And this may be small for particle samples. This is on scaling, so it's real description, even if it's just a scheme. And it's not just pure chance. It's because what are our preferred protein, what is it made of? In terms of chemical compositions, you have carbon, nitrogen, oxygen, hydrogens, and the occasional sulfur if you're lucky. And that's about it. And water is oxygen and hydrogen. So, as you see, the electron density is close and the contrast will be low. So, our solutions of particle macromolecules are poor scatterers. And just to give you an order of magnitude, this is not physics, it's order of magnitude, but it's part of physics as well. The 1 mg per ml solution, and you'll see it's typically what you'll be studying, the order of magnitude again, of a globular protein 15 kilodalton molecular mass, such as lysozyme, myoglobin, or whatever, maybe the protein you're working on, will scatter in the order of 1 photon per million incident photons. So you see, you send 1 million photons, and you get 1 on your detector, which is something useful for the whole 3D image. It's not a lot, and that's why people come and work on storage rings and take the pain of building very complex machines. It's because you hear fantastic X-ray beams with a lot of photons. You've seen the numbers, probably already forgotten about it, but it's 10 to the 13 photons per second. So basically, you still have 10 to the 7 scattered photons per second, which is not bad, actually. So that's why people come here. That's why Italy has been handled for quite a while. Now, one consequence from being in water, beyond the low contrast and scattering power, is that you never do a unique, single, isolated scattering measurement. Never. You always, at least, the very least, do a pair of measurements. You will collect the scattering by the sample in the measuring cell, I sample of Q, and then immediately after or before, or ideally both, and that's what you'll be doing here, I guess, you will be collecting a buffer scattering that is identical, the very same buffer. By very same, I mean not nominally 100 millimolar NaCl, but it's either the elution buffer or dialysis, but it is the same buffer. Nobody is good enough to really produce 2 buffers identically. And the same buffer, and then after proper scaling, you will subtract this buffer from the sample scattering, and you will get the best possible approximation to your the scattering of your particle in solution. And when you do this subtraction, you're not only eliminating the contribution from the buffer, but also from parasitic background, from slit, sample holder, and so on, which in turn should be reduced to a minimum because that scattering by our solution is very low. In fact, you must realize that the scattering is the difference, except at a very small angle, the difference between 2 large numbers, and it's a very small value. So it's very demanding on all scaling, normalization, and so on. It's not a trivial problem. For you, it's transparent, but for the responsible of the beamline, the design of the beamline, it's quite a challenge. So we've seen the scattering amplitudes and intensity expressions, and I just recall them using here delta instead of rho bar simply, but they are identical. Okay, so it's delta rho bar, the electron density contrast. And now the most important consequence from being in solution. That's really important. But particles in solution can't keep quiet. You are perfectly quiet. Nobody's moved for half an hour. But molecules in solution tumble happily around. They don't care. So there is no well-defined azimuthal orientation with respect to the direct beam. Only the angle of the scattered photon can be defined. So only the spherical average of the scattered intensity is experimentally accessible. I already mentioned spherical average 2 or 3 times. So you start getting that feeling of why. And it's really a true circle average because it's true we have double average through time during the measurement for a given molecule. And remember, rotation times, typical are in the nanosecond range for a protein, while the measurement time is from tens of milliseconds up to seconds, and at any time over all particles in the solution. And you probably don't get quite, if I ask you how many molecules you have in 100 times 80 micron square cross-section of the direct beam crossing the sample, nobody will tell me the proper number, I'm sure. Who knows? Maybe one or two. In fact, it's of the order of, well, plus or minus a factor of 10, say, 10 to the 15th, because Avogadro is a really large number. So, basically, we do have a twofold average. So, there's no way you can recover it. Okay. No hope. So, the sample is called isotropic. And as you see here, it's identical in all directions. And clearly, the only variation is along that is radial, along the distance corresponding to the angle between direct beam, the center, and scattered rays. And the vectorial three-dimensional scattering intensity distribution I of q, where q is a vector, reduces to a scalar, which means one-dimensional intensity distribution I of q. And this I suppressed the bold character to emphasize the scalar character of q. So, and that's why after here azimuthal averaging, you get a continuous one-dimensional SAXS profile. So we have here answered our second initial question. We know now why we can speak about SAXS pattern. Okay, immediately did it in this introduction, but without explaining why, just take it for granted. And this spherical average, this reduction to a scalar function, entails a loss of information, which is certainly the most severe intrinsic limitation of the method. We lose information we can't recover. And that's why the information content, I don't have time to delve into this into any detail, but it's limited, and that's why if you only know the scattering pattern of a particle, even if you know it is the scattering pattern, I'll come to that point in a minute, it's difficult to do much about it ab initio. Dmitry, I guess, has done the best with it. He's not the only one. And in fact, a lot of things, a lot of extra information is introduced into any modern attempt. And rightly so. So, we have to be aware that it's not derived from the SAXS pattern, it's extra information. So now, we will try and derive the expression of I1 of q. I've added 1 to specify it. The intensity scattered by one particle in solution, to derive this from the electron density distribution, rho of r. So, I1 of q is the spherical average of I1 of q vector, which is the product of f1 of q and its complex conjugate. So we have a spherical average of this product. If you remember that the product of two functions is the convolution product. So, f1 of q is, remember, the Fourier transform of delta rho of r, and f1 star of delta rho of minus r. So, the product of two Fourier transforms is the Fourier transform of the convolution product of those two functions, delta rho of r star delta rho of minus r. And this should ring a bell. I spent a lot of time at the beginning, but now we capitalize on it. We're really just deriving things in row. So I1 of q is the Fourier transform of this, which is gamma of r, the autocorrelation function. And so it is this expression. Now, we have to perform the spherical average operation. If we use polar coordinates, dvr is r squared, sine theta, dr, d theta, d phi, and the spherical average of exponential phi qr, the imaginary exponential, is sine qr over qr. So that finally the intensity I1 of q is equal to 4 pi coming from sine theta, d theta, d phi integrated over pi and 2 pi range. R1 of q is 4 pi sum of r squared gamma of r, right here. That is p of r sine qr over qr dr. So we've established a relationship between R1 of q and p of r. And reciprocally, p of r can be derived from R1 of q. P of r is r2 gamma of r, and it's given by this related expression, r squared over 2 pi squared, sum 0 to infinity of q squared I of q sine q over qr dq. Good, we store them and we'll come back to it later. Now, I want to introduce, we've spoken about the solution, the particles in the solution. Now we will speak about the solution itself, the containing particles. And we can define two very absolutely central properties of the solution. That is, monodispersity. First, what is a monodispersed solution? It's a solution which contains only identical particles. So there's only one protein in one oligomery state. And it's not a mixture of monomer dimers and higher order oligomers or even aggregates or whatever. You want one particle. It could be all trimers or whatever, I don't care, but they should be identical. If not, when we speak about polydispersity, and then it can be in terms of size or shape, and most of the time it's size and shape. The second property is ideality. An ideal solution is a solution in which there is no intermolecular interactions, macromolecular interactions, that is. We're not speaking about molecule of water, but in terms of the proteins. So I shouldn't say no interactions, I should say no detectable interactions. They are negligible. You always have them. So in this case, there is no correlations between particle positions, and each molecule will scatter X-rays independently from all others because there is physically no probe of all of the molecules. A non-ideal solution is a solution in which there are detectable interactions between non-negligible between particles. In that case, the forces will exert on each molecule due to the neighboring ones will alter the position of the molecule. There will be correlations between particle positions. And Dmitry mentioned it, referring to course two lectures on Thursday or Friday, I don't remember. Anyway, where you will hear about interactions. You can study interactions basically for the sake, because you learn how molecules interact and what are the consequences, which can be even biological. I don't know if you hear about this later on. For instance, the crystalline in your eye is transparent up to a certain time because of interactions between molecules. So it's biologically really relevant. And, oh yeah, true, it's next one, I missed it. So I'll come back in a minute to it. Let's look, before looking at interactions, at the case of an ideal and monodispersed solution, both. In this case, the molecule is ideal, the solution is ideal, so there is no interaction, all molecules scatter independently, and you just write that the intensity scattered by the solution is the sum of intensity scattered by all particles, all kind of particles, ij of q, and so on, weighted by their number or concentration. If the solution is monodispersed, then this equation can be simplified because whatever j, there's only one kind of particle. Whatever j of q is I1 of q. There's only one kind of particles. So that combining both relationships, we end up with ideality, and in the case of ideality monodispersity, the intensity scattered by the solution I've written Ix of Q. It's the experimental, what you measure experimentally, is equal to I1 of Q, intensity scattered by the particle, because there's only one particle in solution, multiplied by the concentration or number of molecules in the solution. So this is trivial, very simple, ideal relationship. That's what you want. You measure something and it's just what you want. That's a problem, a major problem, because it's too simple, so you forget about it. And you take for granted that whatever you measure, Ix of Q, it will be equivalent to I1 of Q. So, really to insist on it, I'm heavy, I know it's on purpose, and I'm wasting time, but it's on purpose. It's really okay, I don't care, I know, I'm not doing measurement anymore. Ix of Q is what you measure, you'll be measuring tonight or tomorrow, from your sample in your apron of tubes, nicely stored at the right temperature. And you will get recording buffer, sample, and so on, Ix of Q. Is that what you want? No. Can you learn something from this? Now, if you know nothing about it, just, I've done that on the lab line with my sample and I've got Ix of Q. Personally, I can't do anything with it. I can just suggest this and that, but I will ask questions, essentially. It's not what you want results. And I can't do anything. I don't think even Dmitry, who is the top of the reference of all possible scientific units when scattering, can do anything with it. But what you want is that, I1 of Q. If you get this, then you can derive something about the shape of your object. If it changes in condition, then you can model the conformational change. You can do a lot of things, all what you'll be learning about during this week. But to do this first and do real science and not just producing garbage, you need to ensure that your solution is both ideal and monodispersed. If it's not, then there's no way from Ix to go back to I1 of Q. And this is something that is your responsibility. It's not X-ray scattering business. One must check independently from X-rays both the validity of both assumptions. And it's absolutely crucial for correct data interpretation because, as I showed, and as you already understood, if you have instructions, if you have mixtures, then this will distort the scattering pattern and you will assume that it is that of your molecule while it's not. So, of course, one needs a well-established and checked purification protocol. You must be sure that you only your molecule and nothing else. Second, that you only one molecular type. So you can check this by selection chromatography, dynamic scattering, analytical personification, mass, and so on. To kind of that a bit earlier. Thank you. Ideality is reached by working in buffers with screen interactions. For instance, if you have charged molecules, you will increase the ionic strength to screen interactions with molecules, and or at high dilution. And in practice, what we do, ideally, we work at infinite dilution, and then we have no interaction, but if there's only one molecule, the signal is not really that bright. So, in practice, we could mention it later after the lecture. In practice, measurements are done at decreasing concentration, and one will check whether there is any dependence of the scattering pattern on concentration. And for instance, here you have 4 dilutions from top, the green one, most concentrated, to the blue one. And you see it's more diluted, and you have already noticeable noise in the large angle region. Now, if you scale them to concentration, you obtain superimposed curves, except the very small angle regions. And there you have clear differences. It's a log plot. Really, small differences are meaningful. the green one is lower than the red one, the magenta, than the red, and then the blue in turn. So here we have interactions, and we must correct for them. In fact, and that's what I wanted to show you earlier, interactions are obviously of two kinds. They are either repulsive or attractive. It's difficult to think of anything else beyond the absence of interaction. Repulsion, typical cases, Coulombic repulsion, or those other cases, where molecules tend to move away from one another, but by moving away, they will get closer to the one in the back. So finally, you will tend to a situation in which molecules are at a roughly common distance from one another. And in this case, you get from the blue curve, 3 mg per ml. It's a case of Coulombic repulsion. It's very low ionic strength. And you see already at 3 mg per ml, you have something like a decrease at very small angles. And then when concentration is increased up to 92 mg per ml, you see that the maximum is shifted outwards to larger Q values, and the peak, the upper peak, is getting sort of narrower with time. This is due to repulsion. This is the effect of repulsive interaction. Very strong one, I emphasize it. The classical effect, which is the parasitic one. Here we were interested in the actual interactions, and this will be dealt with by, I guess, it's Piotr Konarev in 3 or 4 days' time. But here it's what you commonly encounter. Okay, it's much, you don't have a full-blown peak, you tend to minimize it, but there's some residual interactions. And the other one is case of attraction, where molecules tend to clump together. And here you see a case of a protein with attractive interactions which are increasing when you decrease the temperature from 30, the blue one, to 10, the red one, and you see it's not negligible, it's not a marginal effect. But okay, here again, we choose conditions where we maximize these interactions. But you might find in practical what we call residual attractive interactions, where you have just a small change, but it is very significant, and you will understand why later on. So, more about interactions in a few days' time, but what you remember is interactions distort my scattering pattern, so I have to make sure that solutions are ideal. And a major step towards the obtention of monodispersed and ideal solutions was made essentially, I would say, about 10 years ago. There were some attempts a bit earlier, 4 or 5 years before, by one group, which was a one-off experiment, while here the instrument was designed from its inception as ready to be working in this so-called SAXS mode, size exclusion HPLC, which is in line with the SAXS instrument. And here, instead of loading, you will hear about it into all details, and you will actually be doing it later. But instead of loading a sample directly via a robot into the measuring cell, you will load it on top of a gel filtration column, and during the elution, molecules will be separated according to mass and shape. You have a chromatogram with a UV detector at 280 if it's proteins, 360 if you have nucleic acid, and a few seconds later, that sample will go to the SAXS cell, and having separated, for instance, various oligomers, then you have the probability of a monodispersed ideal solution is really much increased. And it has made a lot of experiments possible which wouldn't have been possible otherwise. So it was a great significance, a great project, a great progress, in the field. And now most beamlines and storage rings offer this possibility. So now just, I could spend half an hour on this. I guess the SAXS mode of operation is really a major step, and it's difficult to be sure that your sample is actually monodispersed. And here, it's, so to speak, an order of magnitude higher probability. Now, I just want to mention what I call the basic law of reciprocity in scattering, which is just a direct consequence from the Fourier transform between rho of R and I of Q. But I will present it again vividly. What is it? It says that an object with large dimensions in real space will scatter X-rays essentially at very small angles, with a very large dynamic, a very fast decrease over a small angular range. And in contrast, an object of small dimensions in real space will scatter X-rays over a much broader angular range. Okay? The scattering intensity will be spread over a large angular range. And just to illustrate it, in terms of particle macromolecules, if we think big, we think virus. Virus are particles, biological, and they are big. So here is a rotavirus. Actually, we focus on the virus-like particle, 2 layers, VP6, VP2, and the diameter is 700 angstrom, so really respectable. Molecular mass is 44 megadalton. Sorry, in red, you see the scattering pattern, and you see that indeed it will exhibit a very sharp decrease by almost 4 orders of magnitude over a small angular range. You also see, in passing, regular maxima and minima, which are due to the fact that it's a sphere, it's a property of the Fourier transform of a sphere, and some others are due to the fact that the surface is not, smooth, but convoluted with regular trimers protruding radially. So we have a strong modulation gives rise to this series of nice, well-resolved beams. In contrast, the small object, I've taken lysozyme here. Dmax is 45 angstrom. It has been carefully drawn on scale with the virus. And you see it takes 3,000 lysozyme molecules to get the molecular mass of the virus. And if you look at the scattering pattern in blue, you see that indeed it decreases by less than 2 orders of magnitude over a much broader angular range. So I hope this is now engraved vividly as a vivid recollection for you to remember. And that's the end of the second part. Good. So, data analysis, and now, sorry for that, again, 3 parts. So, it's not finished. And we start with the Guinier analysis. I won't introduce on the Guinier. No, it's not the same picture. You remember anyway. So Henri Guinier can be considered the inventor of the method, and he was working in Paris. Later, he was dean of the university in Orsay, where actually I'm working for the moment. And Guinier was a crystallographer and smaller scatterer, was going to be a smaller scatterer. And also he was an experimentalist and a theoretician. And by examining really lots of, I guess he was doing just with films and so on, trying to analyze the profiles. He proposed, and also doing calculations, so he could put both together. And he stated what's called the Guinier law, the scattering intensity of a particle, underline, can be described by a Gaussian curve in the vicinity of the origin. Every word is important. I will underline another one later on. Here, there's one thing which is a bit, say, unsettling, which is the word vicinity. What is the vicinity of the origin? You realize it means 0 in surroundings, but how far? Is it a narrow neighborhood or a broad vicinity? Actually, the validity domain depends on the precise shape of the particle. This can be mathematically derived very clearly. We won't have time to do that. But let's say that a rule of thumb that it holds true for Q smaller than 1.2 over Rg, or QRG smaller than 1.2. RG is called the radius of gyration, and we will introduce it in a minute for a globular shape. So, you see, the domain depends on the specific shape. So if you don't know the shape, it's difficult to know the precise validity range. But overall thumb, you start with QRG smaller than 1.2, and you look at it. And you see whether you have a Gaussian or not. So the mathematical expression of a Gaussian is given here, with I0, the pre-exponential term, extrapolated density at the origin, and the exponential term here, the Gaussian, minus Q squared, RG squared over 3. So the width of the Gaussian is given, is function of, again, the radius of gyration. Definition next slide. But it's more interesting to use the Guinier in log form. Then we have log, natural log of I of q is natural log of I0 minus q squared RG squared over 3. And of course, if you look at it, you see that plotting log of I of q, versus q squared, you expect a linear variation. And if you perform a linear regression, you will obtain the slope and y-intercept, giving you the radius of gyration value and I0 value. And now we'll get into it. You realize why we use the log version first, because our mind is much better at estimating, evaluating linear variation than any Gaussian. I don't have the Gaussian shape pre-capable in my brain. And second, in 1938 or so, computers were hard to find. You had to do everything by hand, so the linear variation is much better. Good. The radius of gyration, what is it? It is RG squared, the mean square distance to the center of mass of the particle, weighted by the contrast of electron density. So it's what's written here. The mean square, R squared dVr, weighted by delta rho of R, the electron density contrast at the corresponding point. Now, of course, if delta rho of R is strictly constant, again, the assumption we very often make that the particle has a uniform density, or very close to, then RG, we can eliminate delta rho of R from top and bottom, or the fraction, and we obtain RG as a geometrical quantity. And RG is what I call, in this case, an index of non-sphericity. What do I mean by that? Simple. For a given volume, then the smallest RG is that of a sphere. And the radius of gyration of the sphere is square root of 3/5 of R of the radius of the sphere. Fine. Very elementary. Whatever the shape of the object, elongated, flattened, curved, bent, invaginated, whatever, the RG is larger. So, the larger the RG for a given volume, the further away from a sphere you are. Hence, this expression of index of non-sphericity. It tells you whether your object, to make it really coarse and simple, is globular or far from a globule. How serious, how good is this log satisfied experiment? Well, we look just as a Guinier plot, the log of the intensity versus q squared, of a protein, something we recorded on the swinging line close to Paris, where I work. And if you do the linear regression, in blue, the resulting straight line out to QRG equal 1.2, then you get indeed a very good approximation. You realize that indeed Guinier is really working well on good samples, okay, where this is really the scattering of a particle. And in fact, if you look at it, you see it will expand. It's still valid, probably out to QRG equal 1.3 or even further out. It depends, as I said, on the given particle. And just for a solid sphere, for instance, the radius of this approximation holds true only in a very small angular range. It's even smaller, QRG is smaller than 1. And then it tends to decrease very sharply, so you leave the straight line under the line of the Guinier plot. So we've spoken about the radius of gyration, the slope. What about I0? Well, this other speakers will come about it later. I'll do it very quickly. From the intensity at the origin, scaled by the number of particles or the concentration, one can derive an approximation of the molecular mass of the object. Indeed, if the concentration is known, C, because we have to scale by C, the partial specific volume of the particle, and if we know the intensity on an absolute scale, which means the number of incident photons are known, then we can derive an estimate of the molecular mass. And in actual fact, one only gets an estimate of the molecular mass, but it's important because its determination is a useful check of ideality and monodispersity. And I will explain why in the next slide. I just want to say here that this, you should, thinking hard about it, you may have told me that yourself. Why? Because we mentioned that I0 is the integral of rho of R, or delta rho of R, dVr. So the number of electrons squared. If you divide by C, then it's proportional to the number of electrons. And from this, clearly there is a ratio between the mass of the object and the number of electrons, which depends on the chemical composition. So, if you know the protein, you know the chemical composition, or you can calculate it, and from that you can calculate the ratio, and this, from this you can go back to the molecular mass. Okay? I mentioned checking the validity of monodispersity and ideality, because in fact, and that's the end with the Guinier law, practically, the scattering intensity of a particle can be described as a Gaussian curve in the vicinity of the origin. Good, of a particle. Guinier didn't say that if you put any solution of biological macromolecules in the beam, which he didn't do, you will get a nice Guinier and you will get your RG and molecular mass. No. If you have crap, you get crap. But if your solution is monodispersed and ideal, then you have this relationship, and then from the Guinier plot, you will indeed derive the molecular mass. So now, very rapidly, I will present several cases we can observe. Irreversible aggregation. This, and all this are real case, real data. This was FedEx experiment, never try to avoid it. So we got shipped from a colleague, nice samples, we centrifuged them and so on, and we put them in the beam, and we got, this is not a scattering pattern, by the way. This is a Guinier plot. We said it was linear, it's not really linear. And if you do on any region a linear regression, you get I0, which is 700 times what you expect. So clearly it's all aggregated, and here there's nothing you can do. You've wasted your time. You just say, okay, well, I will call my loss. You say, that's it. You just destroy everything and do something else. Experiment again. The second case is more frequent. You do your experiments and you get something like this. So you have not orders of magnitude up or downward curvature. You have a slight upward curvature in this case on the protein. And here you have slight attraction. It's not, you can't use it, but it's not hopeless. You discuss with a colleague, biochemist, and you decide to change buffer. And then you do your experiment again, and you get a perfectly linear Guinier with RG of 3600. So some people, I'm sure none of you would say that, or even think of it. Never, ever. Don't take it personally. But I met people who would say, oh, it's not so bad. Look, we have 5 points here, practically aligned between the dot dash line and QRG equal 1.2. So we do have a small region which is linear. We can derive our RG value. But here, if you do that, you get RG equal 38 angstrom. So it's way too high. It's only 2 angstrom. Okay, it's not 18. But from what you've seen earlier, you realize you can derive RG values within a small fraction, a few tenths of an angstrom. So 2 angstroms is not acceptable. And you will derive wrong conclusions from your measurements. And finally, from time to time, it's all too rare, you get the ideal case. You have 3 solutions, 3 concentrations, you do 3 experiments, 3 Guinier plots, all identical, all perfectly linear out to QRT equal 1.3, no interactions at all, so there is no difference at all in scattering pattern with concentrations. So you can carry on, take the best, statistically speaking, curve, highest concentration, and carry on with Guinier analysis and modeling. And finally, the worst of all cases, this one. So, it's a study of an RNA molecule performed a few years ago with colleagues, and we got first concentration. We were very happy. Perfect Guinier plot, perfect linear, no problem at all. With a relative direction of 49.3, it's a big particle. Okay, we were happy. But we know that we need to do, so we've done dilution series. So we do a twofold dilution, we get again perfect linear plot, and RG 56.6. How come? Christ, look, it's linear, it's the same molecule diluted twofold, 56. So we want to check. So we do a twofold dilution. And here again, perfectly linear, but here it's 59.9. Where shall we end up? And another twofold, and then we get 60.8. Again, it's linear, it's very nice, except for the first point, so there's some subtraction problem, because it starts to be really dense. So, indeed, what happens here, it's a case of repulsive interactions, because this is an RNA, so it's an polyelectrolyte. Even with the high ionic strength we had in the solution, it was not enough to screen all interactions, and there were severe repulsive molecules. But what you will see is that even in the case of severe electrostatic repulsions, we do have, or we can have, linear Guinier plots. So the conclusion is the linear Guinier plot is a requirement. If it's not linear, you throw it away. But it is not a sufficient condition ensuring ideality nor monodispersity of the sample. Good, enough with Mr. Guinier and the central part of the scattering pattern. So now we'll have a look at the other region, the other end of the scattering pattern, the asymptotic trend and large angles within the small angle approximation. This is work done by Günther Porod, who was working in Graz, a town in Stein, in Austria. Beautiful town. And there was in the 40s, in the 60s, 70s, big group studying polymers and in relationship with powerful chemical industry. And they were using X-rays, X-ray scattering, and they've done a lot of work on this. So, Porod he was interested in the asymptotic trend of scattering patterns. And he considered the case of a uniform electron density particle, which on top of it had a sharp interface with the solvent or the matrix in which it was dissolved. So it's a twofold problem. You have rho p within the particle constant and rho 0 with a sharp heavy side, say function on to go from rho 0 to rho p. Good. Porod showed that the asymptotic behavior is given by this equation. The limit is equal to 2 pi s delta rho squared q to the minus 4. Q to the minus 4 is what is important. It means it's a very fast decay as a function of q for a uniform particle with a sharp interface. And S is the area of the solute-solvent interface. So that could be of interest if you want to model geometrically your molecule by a geometrical shape. Knowing the surface of the area of the interface is a great parameter. It's very useful. The problem is, in fact, for proteins, it has limited applications. for two reasons. The first one is that proteins don't have, properly speaking, uniform density. They are short distance density fluctuation, internal fluctuation. Some regions are slightly denser than some others, giving rise to internal contrast and then to scattering. And since it's internal, there are short distances, it will be sensitive at larger Q values, and then it will alter the Q to the -4 trend. And second, we have uncertainties of value of Q at large Q, because remember, 1 photon per million, and they are all in the center, so in the outer region, it's a few per mil, at times even less, that you measure the difference between sample and something. So there is some uncertainty here. And in fact, it's essentially used to introduce a corrective constant factor, V, to the intensity. You measure I of Q, I1 of Q, and you will determine the constant giving the best approximation in terms of Q to the -4, which is supposed to be followed by a uniform density object, and you get I1 star of Q, and this you will use to, for instance, determine the ab initio shape of the object by a variety of programs, and they will be presented in 2 or 3 days, 2 days, I guess. So it's of interest, but just more as a corrective tool. Porod also gave his name to another quantity called the Porod invariant. So this is the expression we derive of P of R as a function of I of Q. For R equals 0, gamma 0 is equal to this expression here. And this is equal to 1 over 2 pi square, constant, and then this integral, which is called capital Q. This is the Porod invariant, and we'll see why it's called Porod invariant and what we can do with it. By definition, gamma 0 is sum of delta rho square dVr, that is delta rho square bar times the volume, where delta rho square bar is the mean square electron density contrast. So Q depends by combining these two expressions of gamma 0. Q is equal to 2 pi square delta rho bar V equals, of course, by definition, sum of 0 to infinity. So that this quantity here, this integral quantity, is invariant because it doesn't depend on the specific shape of the object, but just on the mean square electron density contrast. It's not of interest to us, but if we consider now the case of a uniform electron density particle again, then Q is just simplifies down to 2 pi square delta rho square, which is constant V. And you remember that I0 is the square of the number of electrons of contrast of the particle V delta rho square. So from the ratio, you derive the volume of a particle of uniform density, V. So it's a useful relationship. Proteins are not particles of uniform density. But if you do the correction, you have a good approximation of using the I star of 0 and Q star with the corrected, after subtracting the correction constant, the Q star integral, you get this expression V, and you can from this derive a crude estimate of the molecular mass, which is independent of the concentration. We could derive the molecular mass from I0, knowing the concentration. It's I0 over C, which is proportional to M. Here, you don't know the concentration. You've only done one scattering pattern, and you can derive an estimate of the molecular mass, M equal V over 1.5. So this is useful as an independent and very different way of determining the order of magnitude. Another procedure, so based on Q, has been developed to derive an estimate of VNM independent of the concentration. It's the work some years ago of a Brazilian group, and it's an empirical approach using what we just saw. That is, they've calculated a scattering pattern from 1148 proteins from the PDB of various molecular masses, and they try to estimate the truncation, because you never calculate the scattering pattern to infinity, and the integral for Q is going to infinity, so you have to correct for that. And also the effect of fluctuations, as we said. So instead of doing subtraction, which is a crude way, what they've done is to calculate what we could call Q star, the integral, hence V prime Q max, out to Q max, sum of 0 to Q max. And Q max is 0.2, 0.3, or 0.4 in terms of functional magnitude. And you see in the three colors, the three Q max values, and if you look at the 1150 or so results, three colors for three Q max values, you see roughly you have a pretty good linear behavior, dependence between the apparent volume, V prime, which depends on Q max, and V, the real molecular volume of the particle. And from this, they used this approach to apply it to 21 experimental curves, and they got the an average error with respect to molecular mass of 5% or so, and they were all below 10%. So again, this is a convenient approach. It's not something which gives you the mass as you do from as you derive from a mass spec experiment within 10 to the minus 4 or 5 accuracy. Here it's about 10%, but it's important. Another thing, and it's available on a website. Now, another procedure also based on empirical observation of correlations. It's very empirical between integral quantities derived from the SAXS curve, such as the Q quantity, Q square I of Q, from the SAXS curve and the molecular mass has been proposed by Bob Rumber and John Taylor using so-called volume of correlation, the ratio QR. And they obtain results which are roughly comparable to what you see. People have obtained has been obtained from the Brazilian group. Very recently, a last procedure has also been put forward by Daniel Franke from the local group here. I will say a word of it, otherwise I'm already 15 minutes late. And at that point, it was tempting to combine all those independently developed approaches, empirical approaches, in a statistically rigorous way. And that's what Daniel, Nelly, and people from Dimitri's group have tried to do. And they've presented this approach, which is implemented now in the last SAXS version you will be using. So you will see how it works in practice when doing your data analysis. And details hopefully will be provided in subsequent talk. The take-home message for all this is simple. One should compare the estimate from I0 over C and those above independent from concentration to ensure the consistency of all your data set. And it's always useful to control with complementary techniques such as SECmax, for instance, this is always a good thing to do. Now, let's quickly go through the Kratky plot. Kratky was the head of the lab in Graz. He was also Austrian, also doing polymers and so on. And he was interested in knowing whether the particle, the polymers he was studying, were in a good solvent, in a theta solvent, or in a bad solvent. And knowing whether they were structured, ready to collapse, or whether they were very unfolded. And for this, if you look at log of I of Q versus Q, things are different, but it's difficult to be very definite about it. In contrast, if you plot Q square I of Q versus Q, so nothing's done. Essentially, it's just a representation. Then you see something more, things are clearer. For a folded, in red, folded protein, you see a maximum. So you have a bell-shaped curve, because at the end, you will go down to 0 through the Porod law, Q to the minus 4 or Q to the minus 3 point something, if you have fluctuations in it. So that's the Vachette curve, the asymptotic trend. For a random polymer chain, we expect a plateau at large Q, because one can show that this has an asymptotic behavior due to the minus 2. So it's what you would have. This is a partially folded in cyan. So you see the plateau, the maximum is much shallower, in less clear. And for a protein which is unfolded, random, you get something like the green curve. For a fully extended polymer chain, you even observe an increase at large Q values because the asymptotic trend is in Q to the minus 1 point something. I skip this. Instead of plotting the Kratky plot directly, what is useful is to plot a dimensionless version of it. And instead of plotting Q square of Q, you plot QRG square, dimensionless, IQ over I0, so it's scale to I0, it's a ratio, it's dimensionless, versus QRG. And here, you see that all globular proteins, such as the top ones, fall into a common maximum at about 1.1 and 175, square root of 3. In fact, this is nothing but the Guinier law expressed in this plot, and they all have the same normalized Guinier law once you divided it by IQ over I0 in QRG terms, and it shifted the maximum to larger values both in X and Y for very anisommetric molecules when they are folded. But most importantly, if you look at folded, partially or totally unfolded proteins, then everything is clear because you can compare proteins which are of different masses, of different size, because of the normalization process. And here we have 5 proteins. X is a fully structured, fully crystallized protein. In blue, you have the scattering pattern with a return to 0. It's not, as you see, a Q to the minus 4, but it's going down to 0. Then you have 2 cases in green and red of multi-domain proteins linked by semi-flexible linkers. And you have them in gray, XPC, which is an unfolded protein with elements of secondary structure. And finally, AB5 is a protein-rich, fully unfolded polypeptide, which shows, as you see here, a linear increase at large angles. So that basically at very large QRG values, you observe an increase at large values when your protein is going from globular to fully unfolded and extended. Okay? So if you plot your data of an unknown proteins for which you just determine roughly I0 and RG, and you put it on the master plot, you know immediately whether your protein is fully globular, maybe slightly unfolded, some flexibility, or fully extended. The last part of this third part, data analysis, will explain how you can go from what's called the reciprocal space, the space of intensities, the intensities of a few, to real space, the space of distances within the particle. So, you remember P of R, the distance distribution function. I won't come back to it. And basically, we've seen the equation relating P of R to I of Q, so it's just a one-dimensional Fourier transform. Simple, should be no problem. We do this on the computer and it's done. That's not true. It's not true because you see the integral is going from 0 to infinity, and infinity is very far. So even in terms of small unit scattering, it's too far for us. And second, it's affected by exponential errors. So the calculation of the Fourier transform in complete and noisy data require results. Extrapolations are always for results. So try to avoid it. And to lower and higher angles, so as to be able, because you measure data from QE to Qmax, not from 0 to infinity. So this has been a problem for years, for decades, till in 1977, Otto Glatter, who was working in the same Graz laboratory in Austria, came up with a solution. to the problem. And he needed an hypothesis, but the hypothesis was really cheap. It's just, in fact, a statement. My particle has a finite size. So, since it has a finite size, then I don't need to do the integral up to infinity, but out to d max. So I of q is 4 pi sum 0 to d max of p over sin q over q over r. And here it changes everything, because then, on a finite basis, here you can parameterize p over r by a linear combination of orthogonal basis function. Basis function means I take a set of functions. Otto used so-called cubic splines at the time, which are functions with useful properties for what you want to do. And P over R you can describe as this linear combination of such functions. So you know the phi you choose. What you want is the C. If you know the Cn values, then you know P over R. And how do? You just introduce P over R into the expression of phi of q, and you get this expression. Your intensity is equal to this. What you're after are the Cn's, your unknowns, and you have this for all q values. And it's a lot. On a scattering pattern, you get typically a few hundred of those q values. So you replace the Fourier transform of incomplete and noisy data by solving a linear system of equations of unknown Cn's and as many equations as you have q values. So you solve the system by least square method, but it's an ill-posed problem, and then you have to use regularization methods where you minimize not only the chi-square between this expression, the calculated one with the Cn, and the experimental values, you know, but you add constraints with weight here alpha. Determining alpha is not trivial. Determining the constraint is a matter of choice and careful choice. And to go more directly to what we will be using, as you see, it's a few years ago, but a few years later than Otto, Dmitry developed his own implementation of this approach, the indirect Fourier transform, by developing a program called GNOME and using what you call perceptual criteria. That is, your solution must be the P over R, smooth, stable, with the errors, absence of systematic deviations between the inverse Fourier transform, that is, the calculated scattering pattern and your data, goodness of fit, and so on. And here our example, you see here the scattering pattern in blue, in green, the fit, and over there, the P over R we obtain. From the P over R, we can derive the values of two parameters, Rg and I0, and you say, oh, we've already seen that. Indeed, these are the same you obtain from the Guinier plot. But here, this will use the entire scattering pattern, not just the innermost region. And the innermost region, the Guinier region, is the one which is very sensitive to interactions or the presence of a small fraction of oligomers. So in any case, it's a very good control of the quality of your data analysis and data than to do this cross-check by comparing both estimates. In a few seconds, we'll look here at a few P over R's. So here you have the case of an elongated molecule, and you obtain a sharp peak at small values of R, and then almost a linear decrease down to Dmax, which is what you obtain for a geometrical cylinder, and it's very close to what you obtain. Here, model the shape using Dmitry's program. A case of interest, a bimodal distribution, totally unexpected at first. If you know nothing, I told you it's generally a base-shaped curve. And here you have this kind of two maximum. The case of 2 pi is already 6, but when you see the shape you obtain or the crystal structure superimposed, you understand why. You have a V shape with 3 major globules and a distance of about 70 angstrom between both end of the V. So you realize that the first peak is contributed by internal domain distances, and the second one by interdomain distances. And since there is a simultaneous difference, they are well separated, hence this bimodal appearance. And finally, for bacteriophage capsid, so it's an empty sphere, and we obtain this continuous increase and then sharp decrease down to 850, which is the diameter of the particle. And even this is true, this sharp peak here, because the sphere is not fully a sphere, it's faceted. And what you see here, the distance between two opposite facets on the sphere. So, I'm practically through. You've got a series of bibliographic references, and I won't insist because you get everything. You're not going to write it down, so we'll skip it. And late. I mentioned here, so those were about a selection of various reviews on SAXS, various aspects. Here is guidelines, recent publication guidelines to which Dmitry and some others have contributed to help guide how users on how they should publish a SAXS study, what you should provide as information to the reader for the reader to be able to evaluate. And there's the book on SAXS. You've seen small kids already reading it, and you might, I discovered, win it pretty soon with two local SAXS experts who knew a lot also on neutrons, but two experts on neutrons from the island in Grenoble. And what I've tried to provide you with is a sub-advocate for the travel you're embarking on, because you've seen Kratky plot, Guinier plots, POVRs, monodispersity, ideality, and this key relationship. And the method is simple, but deceptively so, and you should be aware of it. There are pitfalls. Analysis in modeling and monodisperse and ideal solution, except the case where you are specifically after the study of interactions, which is different. You know the structure of the protein, for instance. And it's critical to check the validity of these assumptions, otherwise it's just a case of garbage in, garbage out. Napoli, Guido. And in contrast, if you have good quality, validated data, like this one, then you can apply to your system any of the modeling pressures that you will discover during the course and the subsequent lectures. So I hope I've broken my voice not in vain, and that it will help you now to take full profit and benefit of all the lectures you will follow and all the experiments and data analysis you do during the week. And with this, thank you for your attention.